Hello everyone, this is the section 3.4, the later part. The first two-thirds of the material of section 3.4 was covered in Calculus 1. Now, the final one-third portion of the section is about the tangent line to a parametric curve. You already learned parametric curve from section 1.7. So here, we want to study a way to find the tangent line to a curve, which is represented by a parametric equation. So let's say you have something like this, some parametric curve, all right? Parametric curve C. Now let's say this is a point corresponding to t0. So C is given by x equals f of t, y equals g of t. some domain. And let's say your x0, y0 is when your t value equals t0. Okay? At t equals t0. Okay? We want to find the tangent line. We want to find the equation of the tangent line to that point. Now, finding the tangent line equation was easy when you had the curve from the xy equation, because the slope will be just the derivative value, dy over dx, all right? And you have a passing point. Tangent point is the passing point. Slope, tangent, passing point, so point-slope formula. However, this case, you're not given xy equation. You're given parametric equation. Now, is there any direct way of getting slope of the tangent line without finding xy equation directly by solving it? Okay? Now here, suppose that, let me check recording first. Suppose that both f and g are differentiable and x equals f of t is 1 to 1. This means 1 to 1. 1 to 1 function. At least around t0. Okay? It doesn't have to be 1 to 1 all over the entire time interval, but at least around t0 it is 1 to 1. So x coordinate will not be repeated for different t values, at least around t0. Okay? Normally this is guaranteed. If f prime of t0 is not 0, then this will be actually guaranteed. Okay? So this is what we are going to assume. Dx over dt at t equals t0. So we're going to assume this. X derivative at t0 is not 0. Okay? Then, at least we can write locally it is 1 to 1, so we can think of inverse function around x equals x is 0, right? X is corresponding to t0. So, okay, then, therefore your y, which is g of t, g of f inverse of x. So I'm going to call it h of x by defining h is just nothing but composite function of g of f inverse. So this is a differentiable function around x equal. So this is differentiable function. Differentiable function at x equals x0. Right? So we consider y as a function of x going through this f inverse through g. Now, you can go back to t equation if you have x as a excuse me, x equals f of t. Okay, so this is just same as y of t. Y equals g of t, right? Because g of f inverse of f, right? But anyway, so you can consider that y is a function of x, but x is a function of t. Alright, even though we got this one through y equals function of t and t is a function of x through f inverse. So if we consider that way, why am I doing this? Because I want to relate dy over dx. Here, slope m should be dy over dx when x and y is x0, y0. Not dy over dt, it should be dy over dx. So here, we want to relate dy over dt as using chain. Y is originally given by as a function of x. If you consider that, then derivative of outside function times derivative of inside. So it is just like a t derivative of y of, so h of f of t. H prime of f of t. F prime of t. Just like this. This is just a chain, right? So dy over dx must be dy over dt over dx over dt. Whenever dx over dt is not 0. Alright? Which is just g prime of t over f prime of t in this case. This is how you get dx over dt, dy over dx valid. Here, our slope of the tangent line is dy over dx when x equals x0 and y equals y0, of course. That will be corresponding to t0. dy over dt when t equals t0, dx over dt, t0, which means just g prime of t0 over f prime of t0. Okay? So, we can get the slope of the tangent line, even though we didn't actually solve this one for xy equation. Very often that's either impossible or very hard to do. Here, you don't have to do it. You just find the dy over dt, dx over dt, and take the ratio of that. And you can get the slope of the tangent line. Okay? So, example 1. One and only one. Find an equation of the tangent line to the parametric equation, parametric curve C, which is given by x equals e to the t to the third, y equals 1 plus t minus t squared. Okay? At the point E1, where, and the second part of the question is, where does the curve have horizontal tangent, and can this curve have a vertical tangent? Okay. All right. So your dy over dx, first of all we have to find, okay, so xy equals e1 is when t equals 1, isn't it? E to the 1 power, and 1 plus 1 minus 1 squared is 1. T equals 1. Alright? So, first part. Dy over dx is dy over dt, big over dx over dt. Alright? Dy over dt, 1 minus 2t, dx over dt, chain rule, e to the t to the third times derivative inside function, 3t squared. Okay, so slope, dy over dx when x equals e is just this one, alright? When t equals 1, plug it in. 1 minus 2 times 1 over e to the 1, e times 3, negative 1 over 3e. Okay, so that's the slope. And passing point is e1. Therefore, so the equation is y minus y coordinate of the passing point times slope minus 1 over 3 times x minus e. Okay? If you want, you can. So I can 4/3. You can write it this way. Okay? All right. Second. Now, where do you have a horizontal tangent line? All right. Well, from this, dy over dx equals 0 if dy over dt equals 0, but dx over dt is not. 0 over not 0 will be 0, right? So we'll focus on this. So dy over dt, which is, what is it? What is dy over dt? 1 minus 2t equals 0. T equals 1/2. Now what is dx over dt? Dx over dt equals 3t squared e to the t squared. Not 0 there, when t equals 1/2. So t equals 1/2 indeed. Dy over dt equals 0, but dx dt over dt is not. So dy over dx is certainly 0. So that means as a point, e to the 1/2 to the third, 1/8. Okay? And then 1 plus 1/2 minus 1/4. 1/2 minus 1/4, 1 over 4. So plus 1, 5 over 4. At this point on the curve, you will have horizontal tangent line. Okay? What about vertical? Vertical means that m is actually going to infinity or negative infinity as you approach that point. So if this one approaches non-zero, this one approaches 0, this one happens vertical, m undefined. Not only undefined, it just has to go into infinity. Yeah. If dy over dt is not 0, some non-zero finite number approaching, but dx dt equals 0 at that point, then you're going to achieve vertical, right? Now, dx dt equals 3t squared e to the t cubed equals 0. That equation, e to the whatever will never be 0, always positive. That means this must be 0. So t must be 0. There, what is t, dy over dt when t equals 0? What was dy over dt? 1 minus 2t. 1 minus 2t, t equals 0, 1. Oh, non-zero. Yes, it is vertical. Therefore, vertical. Tilde line. So where? At t equals 0. E to the 0 equals 1. T equals 0. So at 1, 1, you're going to have vertical line. This should be enough because you have only 3 homework problems. They can be done from these materials. This is a final 1/3 material of the whole section of 3.4. Okay? Because the beginning 2/3 of the material was already covered in calculus 1. All right. Thank you. And I'll see you next time.